So you have come to the information-based grasp and manipulation planning workshop. My name is Rob Platt. I'm one of the organizers. Sachin Patil is the other organizer. I'm at Northeastern University. Sachin is at Berkeley. Yeah, so I was looking at the papers that have been submitted to this workshop on the plane coming over here, and I was pretty excited about the work that we're seeing today. I think we have great, our invited speakers are terrific, obviously, but I think we've got great contributed papers too. So I'm looking forward to I'm looking forward to seeing what people have to say. Let's see. So let me just say a few motivational words about why I think, in my personal opinion, information-based planning is a great thing to be studying. So there's a significant body of work in robotics that obviously treats perception and planning as basically two distinct problems. So the way this kind of approach basically works is that there's a perception module that reads in some sensor information, and based on that information comes up with some sort of estimate of the state of the system, state of the world, state of the dynamics, state of whatever. And then that information, the estimate of the state of the world, is packaged up into a little box, handed off to a planning system or a control system. That state estimate is treated basically like the absolute God-given truth, and the planning system goes off and does something and decides what to do. And that approach, of course, would work great if our perceptual systems worked, were just very, very accurate and always return the truth. And of course, they don't. So the problem is that there's just a lot of uncertainty in perception of the real world. Who knew? It's hard to perceive accurately the state of the world. So the talks that see today is going to talk about approaches to doing planning that reason about how much information the perceptual system has been able to gather. So specifically, the planning system can say to itself, well, very uncertain about what the state of the world is, so I'm going to be a little more cautious. Perceptual system might be able to reason about what it might do to gain relevant information that could help the system perform better. In general, I think people are waking up to the idea that there's a lot that the planning system can do to be a little smarter in the face of the perceptual uncertainty of the world. So we're really, one way to look at this work is that we're bringing together, we're bringing perception, we're bringing planning a little bit closer together. We know a lot about each of those problems. What do we know about the intersection? So that's my motivation. The workshop today, we're starting now. I think we end at 6:30, right? Yeah. There is a 3-hour break between 11:50 and 3 p.m. There's some kind of sporting event. I think it's a soccer game. Anyhow, so that between 11:50 and 3 p.m. That's a combination of lunch, and we'll resume at 3 p.m. with Ashutash's talk. So I guess that's the main scheduling event. We have 2 poster sessions. All of the posters are displayed in each of the poster sessions. And then the last thing I have to say is that the session, the workshop is being videotaped, and I guess we have consent forms. The workshop's being videotaped, so don't say anything you'll regret.
It's a great way to start. Don't say anything you'll regret. And you know, you mentioned that soccer. It's fascinating because I was just, there was an article in, David Brooks had an article in the New York Times yesterday about that soccer is a game about controlling space. And I never really thought about it that way, but you know, it's interesting because in these things we're talking about robotics, we always think, well, humans are great at this. But you realize actually in a game like soccer, where there's all this uncertainty from a sort of combined collaborative point of view, that actually humans aren't so good. That predicting under uncertainty and state and action is a problem even for humans when they have to tackle something like playing optimal soccer. So we may see someday that goal of the soccer, the Robo Cup, right, which is that robots will beat humans. I think by 2050 is the goal. All right, so what I'm delighted to be here. I love this topic. I think it's absolutely appropriate, and for all the reasons that Rob just said, I want to thank you, Rob, Sachin, for putting this together, for inviting such a wonderful group of individuals here. And in the short time that I have, what I'd like to add is one other ingredient to this discussion, which is specifically the cloud. And what I mean by this is a number of different aspects. I think that the cloud is going to affect robotics, and specifically the issues we're talking about today, which have to do with belief space models, statistically valid models, because there's really 5 aspects I see. One is big data, that the cloud is going to give us access to large amounts of data, and I'll talk about what I mean by that. Cloud computing is going to give us access to clusters of computing resources, so we can do things that were really inconceivable, certainly inconceivable for onboard computing. And then there's a few other things I won't talk about today, but I'm also excited about the idea that the cloud can enhance open source capabilities. We all know about ROS, but I think we're just at the beginning of that. Robot learning, which is the idea of robots starting to share experiences across platforms, so that the collective models will become stronger and more accurate over time. And then this last one is call centers, that basically robots will be able to access humans on demand when they get stuck. All right, so here's one of the scenarios we're thinking about, which is a robot is doing something like decluttering, looks down and sees something it's not sure about, takes an image of that and sends that up to the cloud. And so the cloud then indexes that using something like Google Goggles or Amazon's new Firefly, where it will pull up, take the image, do some processing. Again, that's leveraging all the advances in machine vision and statistical learning, for massive data sets. But it will index into an object. But then, more importantly, not just to be able to send you web pages or a location where to buy that object, but it will also give you information about the geometry and the mechanics of the object, specifically like its center of mass, its frictional properties, and ideally something about how to grasp it. So the scenario is that then the robot can go ahead and do that grasp. And the architecture we're thinking about is something like this, where you're essentially using all the data sets that are coming in all the time. Every time someone takes photographs in the world of objects, and those are being labeled and indexed. So Google is getting better and better, Google or other systems are getting better and better recognition tools. Then we're also supplementing that with all this kind of domain knowledge that may come from, let's say, manufacturers or all kinds of other sources that are pulling up data about the object. But this is really what I want to focus on today, which is the grasp analysis. So this is being done, again, in the cloud in the background. So we're not thinking about this as happening on the fly. So I realize that latency is a problem with the cloud. Reliability of the network is always going to be a problem. But the idea is that we can do a lot of pre-computation for many objects. And then this can be running, just grinding away and generating analysis, so that and this is a scenario when an object is encountered, it goes up to the engine, it pulls down identifies the object and pulls up both CAD models and other semantic information, but also the candidate grasps have been pre-computed. And then with that set of candidate grasps and the pose estimation, that this can be done locally, and we can figure out an optimal grasp from that candidate set. And then I'm also excited about this, which is closing the loop, which is that once the robot executes that operation or that grasp, it can then feed back to the cloud and say whether or not it was successful. And that's very helpful because we can allow that to prune grasps that are not successful in the field. Okay, so the grasp analysis is an active topic, and we'll be talking about it. It's our focus today, really. And there's been a huge amount of advance in this field, and we'll be hearing lots of new perspectives on this. This is, of course, GraspIt, which uses a kind of simulated annealing approach, and it's been fairly effective. I mean, this for generating grasps, it works it seems to converge very nicely from many objects, as you can see here. And one of the things, though, and there is a huge body of research that really dates back over a century to, this is just a tip of the iceberg, just a quick sample of some of that work, that tries to address grasping where from an analytic point of view. There's also work where we have to really add into the model that we don't know exactly where the object is. We don't know the position and orientation of the object in space. Now, so there's been work like this work, and there's also the idea of how can we handle or cope with uncertainty, geometric uncertainty in pose. Now, one idea that we're starting to revisit is the power of sampling. And sampling, as everyone knows, has been extraordinarily successful for motion planning. And there's a huge body of research in this area, and it's really, in a sense, been a breakthrough in motion planning over purely analytic results. The problem is that, and as Rob alluded to, that in a realistic environment, we are faced with things like this, which is the sensory data is still incredibly noisy. We don't know. If we knew a perfect model of the environment, then statistical sampling would be a very effective way of coping with motion planning and I think also with grasping. But we don't know the exact geometry of things. We don't know not only where things are, but it's additively problematic because when we get data like this, we don't even know the shapes of the objects. And this is related to what's known in industry and manufacturing as the tolerancing. And this is this is one model of geometric tolerancing. In other words, this is a nominal shape of this part, but the true shape can vary according to all these different dimensions. That's the way things are characterized in industry. And so the reality is we don't even know what the shape of the object is. So we could have the best analytic model in the world, but it's all predicated on this assumption that we know the geometry of the object. So we've been thinking about this and looking at some of this literature on geometric tolerancing, and I also want to acknowledge that there's an ongoing body of work in this idea of using the cloud, of indexing processing on the fly. In particular, this paper is really exciting. This came out just in December, and it's a model that doesn't mention the cloud, but really the idea of being able to do this is very computationally intensive, of being able to sample different potential grasps in the cloud, and in this case using simulation, and then to do this over many, many samples to be able to pre-compute estimates on what would be the most optimal grasp. And these are fairly time-consuming, but we have a couple ideas about how it could be speeded up, and also this kind of work, again, could be done in the cloud. So I'll give you one example. This is a scenario where we're grasping a part with a parallel jaw gripper. This is the nominal view of the part. So the idea is, however, that the true state of the part is uncertain. So it could be any one of these. These are just some examples of the true object that might be lying there. And we don't know which one it is. And so the question is, where should the gripper be placed? How should we grasp this thing that we're not even sure what its shape is? So the way we're approaching this is to treat that nominal object as defining a probability distribution. So we have this distribution. We want to be able to figure out where to grasp the part. So what we're going to do is look at, again, we're going to consider this as a planar problem, or we're essentially dealing with extruded polygonal shapes. And we're going to consider only quasi-static motion. So we're not going to look at the dynamics. We're going to imagine that the gripper is coming down from above, and the part is sitting on a flat work surface. And what we're going to do is assign a conservative estimate of the coefficient of friction between the gripper and the object. And then we're going to consider this class of grasps called push grasps, been really pioneered by Matt Mason. And the idea is that if there's an advantage to be gained by pushing with one jaw for a certain amount of time before the second jaw makes contact. And the advantage there is that the first jaw can have some effect of aligning the part with one of the linear edges. And so what we want to do is consider what would be the best push grasp for this uncertain object. And it turns out that there's a very nice analytic model for the success. If we know the object, if we have an exact model of the object, then we can use a construction like this geometric construction, and these zones in gray here are basically guaranteed to converge to a stable grasp. The part will move into alignment. And this is a conservative assumption. In other words, there's some parts over here outside the gray areas that will also result in a stable grasp, but we're not going to consider, we're just going to consider the parts inside the gray zone, which is a conservative or lower bound on the probability of success of a grasp. So what we're going to do then is define a quality measure based on this lower bound. And the idea, so this is whether this is a force closure or not for this particular grasp. And what we're doing now is sampling the shapes from that shape distribution. And when we do a sample, it has associated probabilities based on where we are and from each of the vertices, how far they are from the nominal median or mean, and that gives us a associated probability with different shapes. Then we take each of those shapes and we run it through that analytic model, and we see if it succeeds or not. And then if it does, then that gets added in with its associated probability into an estimate, a lower bound estimate of the quality of that particular grasp. That is, for that particular grasp orientation and position. Now, this whisker diagram here is a way of illustrating this. Each whisker represents a grasp at a particular nominal contact position and orientation of the gripper. So, and the gray is showing you is trying to illustrate the range of different parts that were sampled. Yes, Kostas.
Is there an assumption here that the uncertainty for each vertex is independent?
Yes. Yes. Right now, yes. So and this is a strong assumption. There's a number of assumptions. Another one I should have said is also that we assume that there's uncertainty in the vertices, but we also have linear connection, that there's perfect linear lines between each vertex, which also is not true in practice. But yes, we're assuming they're independent. So the idea is that we're going to sample across this big space of grasps and the big space of shapes. And the goal is, once we perform these samples over essentially the cross product, the convolution of the action space and the shape space, what we want to do is find the optimal grasp, the grasp that maximizes the minimum probability of success. Yeah.
So you also assume that the grasp itself is rigid, perfectly rigid?
Yes.
Because of the alignment. Because normally if human fingers would grasp something, the finger aligns with the object rather than the object aligns with the hand.
That's true. That's true.
But you assume rigid.
That's true. Yes, thank you. That's another assumption. I got to update my assumptions page. No, you're right. Because we're assuming rigid, perfectly accurate grippers.
Because
right.
to grasp something with a metal glove, that's very hard. Actually.
That's right. Yeah.
Don't say anything new. Don't do that.
Oh yeah, right. No, I absolutely no. I want to emphasize, and I appreciate both these questions, because this is very much work in progress. We're not presenting this as a solved problem. What I'm doing, this is an example of what I think is a promising direction for research, but lots of room for improvement. All right, so then the algorithm, the nice thing about this sampling-based approach is that it's eminently parallelizable. And so we can do these, we can do the sampling in parallel over many, many nodes in the cloud. And so we've been using, there's a number of resources that are out there. This is actually growing every week. There's another announcement about different cloud-based resources. But you know what, these are just widely available. The cost is dropping dramatically. And so this is a terrific new resource for doing these kinds of computations. I'll just show you a couple results, and I should have introduced Ben Kehoe. Put your hand up there, Ben. Ben is this is his PhD research, and he'll take all the toughest questions. This is terrific work that he's been doing over the last 3 years, and this is one of the results, which is these are for different bracket-shaped parts that we found online. And again, you're looking at the nominal part here, and then the Q is the best grasp found. The Q star is the quality of the best grasp, and this is the best grasp for this part, et cetera. And if you look at these, they look pretty reasonable, except this one. This is it doesn't look like where you or I would want to grasp that. We'd probably want to grasp along this axis. But what's interesting is that our intuition is not so good, right? Because we don't actually, it's hard to think about the variation in in the shape and the vertices and the center of mass. It turns out that actually when you do this, many times you get this little edge here will catch, and the part will cause the part to not be stably grasped. So this one was found to be the most stable. And there's some information here about the speed up, how fast we get. We did this on just multi-core machines at first, and you see approximately linear speed up, right? This is what you expect, which is that as we put this on more cores, we can cut down the number of the time proportionally. And here's an example of, for this other part, that little plug. And these are 3 grasps that were considered, and these are the associated lower bounds on the probability of success. What was interesting is we also ran some experiments, and this one that you just saw was predicted to be 83% probability of success, and in the 5 experiments we ran, it worked every time. But now I'll show you the third one. Now, if you just look at it, it looks very similar to the first one. A and C look pretty comparable. Just a little bit of offset in the position and orientation here. But this one was predicted to have fairly low probability of success. And indeed, when we did experiments, that's what we got. It failed fairly often, every time. So this is an example where I don't know about you, but when I look at these, I look and I wouldn't be able to differentiate. Those just look like equally reasonable grasps. But in fact, there is a nuance and the subtlety in the behavior that's very hard to determine intuitively. So as I mentioned, we did some experiments on multi-core machines, and then Ben, working with an undergrad, did an experiment last year where he then ran this with PyCloud in a cloud environment on a number of machines. And the interesting thing here, what you want is you want like a linear speed up, but what happens is you don't quite get that. And the reason is that the cloud is not perfect. And so what happens is not all the nodes return. Not all the nodes converge, and it's not that they're not converging the computation, but they just are unreliable. So we can talk more about this, but it is important to think about, because as we're distributing this computation and putting these processes out in the cloud, we have to essentially add redundancy, because they're not all going to return within a reasonable amount of time. We're now looking at, so what I've mentioned so far is just dealing with the uncertainty in shape. We're revisiting now the uncertainty in pose, in the position and orientation. And here's one scenario, just to illustrate where we are right now, is this is like a tape dispenser. And you might imagine that we're pushing, again, with that offset, the push grasp, on this jaw first, and then that jaw makes contact second. But what we're doing is combining uncertainty now in orientation and position. So this is sort of the extremes of the different poses that we're considering. And we're going to apply, one other thing that's different is we're going to apply a simulation rather than analytic model here. And I'll show you, this is, Ben was able to modify box 2D to be able to do a simulation of different grasp strategies. Here's one that looks good. Now notice, so there's some subtlety to what happened there, right? So it's actually made use of that little flange to align itself. And here's another one that looks reasonable, but fails. So I'm going to show you that one more time really quickly. Here we go. How are we doing on time? We'll wrap it up in a minute, in a few minutes. So that is a stable, successful grasp. And then this is one that looks stable and reasonable, but when you watch what happens, because of the way the center of mass is and the slip, the part actually slips away. Yes, Sherman?
Why did you switch to simulation instead of the analytic?
Because here it's actually very hard, for pose uncertainty, it's harder to determine. Where we want to also incorporate the uncertainty in slip. That is harder to determine with the analytic model. And here what I was getting at was that from those two grasps, this one that looks like the most reasonable to me, at least intuitively, has actually a lower probability, a lower quality measure than this one on the right, which has, which actually succeeds more often based on these simulations. And I also want to say there's something else Ben just realized last week, is that there's something nice, which is that when we're dealing with uncertainty in pose and gripper orientation, they're actually dual spaces. So in some cases, the uncertainty in pose is actually exactly equivalent to the uncertainty in the gripper position. So if we're smart about the sampling, we can make use of that. So we can reuse samples from that space. And this is where I think we have enormous, there's enormous opportunities, which is how do we start to become much more efficient in the sampling. The cloud gives us access to vast amounts of resources, but just doing brute force sampling is not ideal. All right, so there's a number of papers that have on the related topics on this that were coming out of the group, and we have work on a couple more. Very quickly, I will say that we're also very interested in work in belief space, and we're doing some thinking with Sachin and the others, with Pieter, Abbeel, Sachin, on how we can incorporate belief space into this kind of model. And last thing I'll mention is that we're doing some work with Jeff Mahler and Michael Lasky on a model of incorporating GPIS, Gaussian process implicit surfaces, into grasp analysis. And we have some ideas that also may benefit from parallel computing in the cloud. So with that, thank you. Questions, Jeff?
I have, it's more of a comment. I want to emphasize something that you said in a little bit different way. And
okay.
One of the things you said in the beginning was that we have to have perfect information to apply grasp analysis. And in kind of a negative connotation on having all that perfect information, which we don't. But then you did come around and under assumptions within your probabilistic model, then you did apply the grasp analysis. So I want people to come away with this realizing that even when you have to know all the information, it's still useful. Because even though you don't know all the information exactly, then for each instance of whatever you're considering, you say, this is my exact information, I'm going to do my analysis. And one other thing that your pictures made me think about was you can actually apply the typical grasp analysis if you, for example, use an RGBD camera. All you really need to know to apply grasp analysis is where you're going to touch it, and approximately where you're going to touch it, and approximately what the normal is. And so that I think could open up the use of the old style, know everything exactly analysis to the uncertainty that's becoming much more important than it was in those days when we did that stuff.
So are you, just to understand the last thing you said, you need to know the contact point and the normals?
So like for force closure,
Yes.
you need an estimate of position of the contact points and the normals of the contact points, and I guess really the friction coefficient. Right? And you don't have to know the intervening geometry that's
Right.
not in contact. That could be anything.
That's actually really interesting because that's very relevant to the things we're thinking about with the GPIS. Exactly that we can have very high uncertainty in parts that we're not necessarily making contact with.
Right.
We don't have to spend a lot of time or worry at all about that. We can focus in, and that's where some of this active sensing comes in, because you can move to get that, to acquire the information at the critical points, and do have hypotheses about where those are. Very good. Thanks.